Good morning, everyone, and a special good morning to our genius, Mr. Abdul Karim. Now, today we're going to discuss the physics behind bouncing balls. Now, in order to do so, we need to understand the forces that enact on the ball, which are acceleration, velocity, and gravity. Now, gravity is a unique force. That is because of the consistency it has no matter the state of the object. Whether it is falling in midair or simply resting, the object will always have an acceleration of 9.8 meters per second squared towards the center of the earth. Now, you might be asking yourself, well, why am I not plummeting through the earth right now? Well, that is because of normal force. As this pineapple is demonstrating, it is resting on the table, yet at the same time the table is pushing upwards at it with an equal force as the gravity is applying from the pineapple to the table. That's why literally sitting on a chair on Earth feels exactly the same as accelerating 9.8 meters per second squared upwards in a rocket. Now let's discuss velocity. Velocity is different than speed. That is because of the way they're both calculated. Speed is calculated through distance, while velocity is calculated through displacement. The difference between the both is that distance is the literal distance from the pathway that the object took, while displacement is the distance from the initial point to the final point. As this figure demonstrates, the distance is the pathway that the bike took, while displacement is the direct distance from point A to point B, regardless of the path. That is why displacement is a vector quantity, meaning that it follows direction, while distance is a scalar quantity, like time, mass, and temperature, meaning that it does not have any direction. Now let's talk about acceleration, which is the change in the velocity or speed of an object. Now, it can be positive, like this test is showing, or negative, like the BMW braking. Now, this figure is showing an object, which is a ball, going through free fall, which is just dropping from rest. Now, you can see that the ball is accelerating, but the numbers that it's showing may not be exactly accurate. That is due to air resistance. Air resistance is a type of drag force, which represents the force that opposes objects moving through the air. Now, air resistance has multiple factors, of which are surface area. That is why many parachutes are quite large in order to have a high drag coefficient, and speed, meaning that the higher the speed, the higher the drag coefficient, and the shape of the object. That is why many sports cars have weird or unique shapes to reduce the drag coefficient as much as possible. However, a lot of the time in physics, air resistance is essentially ignored. That is because many objects have quite little change due to air resistance, especially, for example, this bouncing ball. Back to the figure. You can see that the ball, again, is in free fall, and in every second the ball is gaining an amount of speed, and speed or velocity is measured in meters per second, and the object is gaining meters per second. That is why acceleration has a unit of meters per second squared. Now, another way you can tell that the object is accelerating is that through every equal time interval, the distance from the previous time interval to the next one is increasing. So from 0 to 1 it's small, from 1 to 2 it's slightly larger, from 2 to 3 it's even larger, 3 to 4 it's quite big, and 4 to 5 it's really big. And that is a representation of acceleration through a motion diagram. Now, this motion diagram represents acceleration of gravity on Earth, which is 9.8 meters per second squared. Now that you have established the basics behind the physics of bouncing balls, we can get on with the experiment. Here you can see that I've placed 5-inch markers from 30 to 0 inches high to mark the placement of the ball at any instant. Here you can see that the first turning point is 22 inches high. Now, the turning point is the instant at which a ball or the object has a velocity of 0 meters per second. That doesn't mean that its acceleration is 0. In fact, gravity, as we stated before, is always constant, Therefore, the acceleration is always negative 9.8 meters per second squared. Here you can see that the second turning point is at 16.5 inches high. Third is at 12 inches high, 9 inches high, 7 inches high, and finally 5 inches high. Accompanied by this adorable ferret, let's answer some questions regarding the experiment. First of all, what is the final velocity of the ball before each bounce? What is the average velocity and speed of the ball? What is the displacement between each bounce? What is the total displacement and distance the ball covered? What is the time the ball took between each bounce? And finally, what is the final velocity of the ball before each landing? Now let's get on to the fancy answers with explanations. Here you can see the table of calculations with its very fancy monocle and mustache. And to the very left hand side of the table, you can see the 5 locations which represent the questions that were previously asked. And then to the top of the table are the 7 segments in which represent the periods at which the ball was bouncing and landing. So from 30 inches high to 0, and then from 0 to 22 and back to 0, and so on. Then to the right hand side of the table is the total / average of the values. So for time, its total is 1.85 seconds, while the velocity has an average of negative 16.21 inches per second. Well, you might be asking yourself, how did I do it? That was really impressive and really sophisticated. Really, how did I do it? Well, it's using physics. I don't know what you guys were else thinking, but yeah, it's quite simple actually. Anyways, I hope you guys enjoyed. Mister, I'd appreciate 100. Psych! Here you can see the 3 equations I used to solve all the questions. The first one represents that displacement y equals half of acceleration multiplied by time squared plus the initial velocity multiplied by time. The second equation represents that the final velocity equals the initial velocity plus the multiplication of acceleration and time. And the final equation represents that the average velocity equals displacement over time. Now, a quick note. Gravity in this scenario equals 385.83 inches per second squared. This is the exact same as 9.8 meters. It's just that I have switched it to inches since the displacement is measured in inches to make sure that all the units were correct. Here you can see how I solved the first question. How did I find time within each segment? Now, I use the first equation to do so. Now, in order to find y, or in other words displacement, we take the final position and subtract from it the initial position. Now, the final position was 0 while the initial position was 30, so 0 minus 30 is negative 30, equals half of the acceleration, which is negative 385, not 9.8, because it is in inches and not meters, x squared plus 0. We plug this into the calculator and press shift solve, and we get that x equals 0.4 seconds. We applied this equation to all the other segments, and we get that the total time that the ball took during the entire trip was 1.85 seconds. In order to solve the second equation, I used the second formula. V final equals V initial plus the multiplication of acceleration and time. Now, since V initial is 0, since it's dropped from rest and free fall, we just add 0 to the multiplication of negative 385.827, the acceleration in inches, times 0.4, the time of the segment, which is the first segment. In all of the following calculations, we're going to use the first segment as an example. Now, we plug this into the calculator and we get that the final velocity before landing is negative 154.3 inches per second. Now the value is negative because it is decreasing its height, so it is going in the negative direction, and velocity is a vector quantity, that's why it can be negative. Unlike time, average velocity is not calculated by calculating each individual segment and adding it all together. Instead, we need to use the third equation, that is average velocity equals displacement over time. Now, in order to find displacement, we need to just add all the individual displacements of each segment. Now, you can see that nearly all the displacements are zero. Now, you might ask yourself, well, why is that the case? Now, the model to the right will explain that to you. You can see that the initial velocity is 131.2 inches per second, upward. So the ball is going upward and then reaches its terminal turning point and starts to go down and reach the exact same point that it was in the previous initial position. Now, we said that displacement is the final position minus the initial position, and here the initial position is the same as the final position. Therefore, the displacement is zero. Now, there could be a horizontal shift that the ball went from one side to the other, but here we're only calculating vertical displacement, not overall displacement or horizontal displacement. That's why now the first one has displacement because the ball started from the top, not the bottom. Therefore, it has negative 30 displacement. And the time, we already know from the first question, 1.85 seconds. So we divide negative 30 by 1.85 and we get that the average velocity is negative 16.2 inches per second. Next is the calculation of the speed of the ball throughout the entire process. So in order to do so, we shall use the third equation again, but instead of v equaling velocity, it shall equal speed, and y shall equal distance instead of displacement. That is because speed is calculated through distance, not displacement. And in order to calculate distance, we just measure the legitimate distance of the pathway the ball took throughout the course of its bounce. So the first one was from 30 inches high to 0. That's just easy, 30 inches. The next one is a bit more complicated. It went from 0 to 22, and then from 22 back to 0. So it covered the distance of 22 inches 2 times. Therefore, the total distance is 44 inches. And that logic is applied to the rest of the segments, giving us a total of 173 inches. So now we have both time and distance. 173 divided by 1.85 seconds gives us the average speed of 93.51 inches per second. Now, the individual speeds of each segment can also be calculated through the same way. Just take the individual distance of that segment and divide it by the individual time that distance took, and you shall get the individual speed of each segment. And I hope you all enjoyed. Mr. Abdul Karim, please give me 100. This took really long time, so I really appreciate it. Thank you, and I hope you enjoyed.